Well, kia ora koutou. I've just had a session for DITA on formal languages and especially grammars, and this is just to share with you some of the key ideas and some of the questions. So, formal languages is one of the areas that students can study for NCEA. And just as a very quick reminder, the whole point of a formal language is that it's languages that are very well defined. So programming languages, a really common form of that. This programming language here, that you know it's a formal language basically if it can give you a syntax error. And the reason for the syntax error is that in this case a bracket has been left out. And so where are those rules that make that possible? Here's another formal language. It's called Hypertext Markup Language, or HTML. This time there's one of the angles is the wrong way round, one of the angle brackets, and so that's an error. And somewhere there's a definition that tells you what direction everything has to be and what you're allowed to put into it. Another formal language is just things like typing in email addresses. So if you've ever used a website, as you start to type something, it tells you if it's correct or not. There's a formal definition for what makes an okay email address. This one ends with a dot, not okay. This is an Excel spreadsheet, and again, it's got an error in it in the formula. It's not complete, and the system says, "Hey, that language is incorrect." So the thing about a formal language, the challenge is that we have a very well-defined language, not like natural languages like English, which all sorts of stuff can happen, but it's a well-defined language. Often it's a programming language, but not necessarily. And we need to be able to check that it fits that definition so that we can rely on it, that if it's an email address, that we're pretty confident it hasn't got silly mistakes in it, like a space or something like that. If it's a programming language, that it's worth trying to make sense of what it is, and that it doesn't have things in the structure that just can't be made sense of. So examples of formal languages, HTML, XML, the L in both of those stands for language. XML is similar, related to HTML, and the X in DocX, if you're storing spreadsheets and PowerPoints and documents and so on, the X there means that they're stored in XML, a formal language. Then programming languages are formal languages. There's things that they can and can't have, and then stuff like email addresses, URLs, anything that's sort of specified in a format. And for the talk, I was assuming people have done regular languages, and most people had already taught that. It's been around for quite a few years in NCEA. But just as a reminder, a regular language is a particular way of defining, it's a kind of formal language that is defined using regular expressions, and the regular expressions generate a finite state automaton to check things. So as a quick example, here's a language of things that Microsoft Excel treats as real numbers. 3.14 is okay. 3 is not a real number, it treats it as an integer. 3.0, that's okay. 3 point, turns out that gets converted to a 3. 0.5 though, that stays as 0.5, that's okay. So maybe anything with a point, well, not just a point on its own, that's not in. 3.1.4, that's not a number. And so at this point, we've got a list of things that are in the language and things that are not in the language of, in this case, real numbers in Excel. Don't use this for everyday purposes, but it's a rough guide. The main point I'm making is that a formal language divides things into what's in and what's out. Now, it's very hard to say exactly what's needed. Maybe it's got a few digits and at least one decimal point, or only one decimal point, or whatever. And a really quick way to define that sort of thing is through what's called a regular expression. And here's one format. It says, digit star dot digit plus. There's another format here. It's 0 to 9 star dot 0 to 9 plus. The star means 0 or more of those things. The plus means at least one of them. So basically this is saying it can start with any number of digits, and then it has to be a dot, and then it must have at least one digit, but you can have as many of them as you want. Now, computers need to have some way of actually checking these things, and that gets converted to a finite state automaton. Here's one that does exactly this check, so it goes to state 1. Any digits, it just stays in that state. But ultimately, we need to get to state 3, which has got a double circle. Okay, so that's regular languages. It turns out that they can't do everything we'd like to do with languages, and so they have their limits. In particular, they can't recognize things like what I've got on the screen here. They can't recognize expressions where you've got, an equation, an expression within brackets, brackets within brackets, and all that sort of thing. Too complicated. They can't deal with, all that nesting going on. The next line is some HTML. Looks a bit ugly all on one line, but it's a list within a list. Can't do that with regular languages. They just don't have the expressive power for that. And then the final one, it's not a very interesting language, but it's a good toy one to start with, where you have a certain number of A's and the number of B's is the same. Now, you'd think, like, you can easily do things where it has an even number of A's and an odd number of B's with a regular language, but you can't do these ones where the number in one half of it is the same as the number of, the number of A's is the same as the number of B's in the second half. Good exercise for your students to try, just to find out what those sort of limits are, and they'll find that they just cannot come up with a regular expression or with a finite state automaton that can do that. So what we need to the rescue is context-free grammars. So the context-free grammar, or CFG, uses a slightly different notation, and I've got it over here on the right. It's made up of productions, and the productions say that, look, we start with the symbol S, and that S can be changed into either ASB, or the S can be changed into an AB. So we've created this sort of challenge game thing here that students can try, where we've got a single S and they have to try and form here AABB. And so links to these challenges are in the field guide, and they're in the draft chapter. I'll make sure there's links of those to go with this. So basically click on the S and it offers the two productions, the two options to replace the S. If I'm trying to form AABB, then if I just replace it with AB, we're stuck. I can't replace anything else. So I'll reset that and I'll try replacing the S with ASB. And now this creates the S in the middle, and I can replace that with AB, get the green light. I've managed to create that particular pattern. And so this grammar here, in fact, is used for basically saying that the number of A's has to be the same as the number of B's. In fact, if the S, if I substitute it with ASB, and I substitute that S with ASB, and that S with ASB, and so on, and then eventually with AB, you can see that it will generate those things. So that's the set of rules that checks that the number of A's at the start is the same as the number of B's at the end. If you were to give something to a grammar that is not correct, so like AAB, then basically I'd say, well, which of these do I use? I can't use AB, that's not going to produce it, so I'll try ASB, but as soon as I choose that S there, of course, it forces it to have the AB in the middle, can't match, and so it's a bit like a finite state automaton that can't get to that accepting state. There is no way of getting there. And that's exactly what happens every time you're typing in, say, a programming language and it says there's a syntax error. Here it might say another B is required, or something like, a B is missing. In a real programming language, it will say there's a bracket missing or something like that. Another example, and again, these are linked from the field guide text. This grammar looks almost the same, but as well as the ASB and the AB, the S can be changed to an SS. And so if I want to form AB, AB, I'll choose S goes to SS, and then now the left-hand S can change to AB, the right-hand one goes to AB, and I've solved it. So you can use these as kind of a puzzle. It's a chance for students to really get to know how these work. The most complicated one we have is for actually building expressions, where you have pluses and times and brackets, and you can have brackets within brackets and all that sort of stuff. So here's a simple one to warm up on. And here's the productions. These are the rules for things that make up an expression, at least ones with plus and multiply in them. So on the left, we've got, this expression is something times something. So it looks like we'll use this production here, that E can be replaced with E times E. So I'll put that in. And then the thing on the left-hand side, well, it's something in brackets. So I'll use the production that E can be replaced with something in brackets. What's in the brackets? Well, it's something plus something, so I'll have to use that production. And what's on the left-hand side? Well, that's a number, and I can see that n ultimately goes to a digit, so I'll replace that with the number 1. The e on here, it's a number, and it's going to be the number 3. On the right-hand side, that's also a number, and that's the number 2. And so now I've found the way to do that. Now, in practice, where's my pen gone? Here we go. Right. So in practice, we can actually draw that process. And in fact, let me just bring up a piece of paper here. So if what I just went through here, if I reset that, is that I said I'm going to use the production E goes to something times something. And so, we start off with an E, and E goes to E times E. And we're kind of keeping a record of what productions we use. And then the left-hand one, that E, I said it goes to E in brackets. So that can go to an open bracket, an E, and a closed bracket. And then what's the one inside the brackets? Well, that goes to something plus something. So E goes to E plus E. And that E there, that went to a number, N. And that number went to a 1. This one went to a number, which is 3. And this one went to a number, which is 2. Pretty complicated for what looks pretty simple on the right-hand side, 1 plus 3 times 2. But this is called the parse tree. And the word parse is really important. It's basically trying to work out how this thing is structured, breaking it down into its components. We also use it for English. Example I used before is if we say time flies, then if we parse this in English, then time would be a noun and flies would be a verb, and that's fine. By the way, context-free grammars can't parse English properly, but it's just the word parse. That means break things down into components. A counterexample is fruit flies, where that whole thing is a noun or a noun phrase, fruit flies. And so although it's the same word, it's got a different meaning in different contexts. And the same happens when we try and parse a formal language. So that's just where that word comes from. A little bit of other terminology. These capital letters, or at least the things I've been using capital letters for, is called a non-terminal, which means we haven't finished our parsing. It hasn't been broken down into something, but the digits here, they are called a terminal. It's in its final state. We can't break that down anymore. Basically, non-terminals are things that are on the left-hand side of the grammar, like E becomes something here, N becomes something. On the right-hand side, it's a mixture of non-terminals, which here are capital letters, and terminals, which include the plus and the times and so on. They're terminals. They don't get replaced with anything because they can't. They're not on the left-hand side. That's all that makes the difference between those. There's a lot of words going on there, a lot of language and so on to talk about languages, but they're pretty standard definitions. They're widely used, and they're things that once students work with these quite a bit and they talk about the terminals, the non-terminals, the context-free grammar and so on, then they hopefully can get reasonably comfortable with that and are able to answer questions about them. So that's context-free grammars in a nutshell. One other point that I want to make is that there's a hierarchy of languages. So I've talked about regular languages, which are the ones that, relatively simple. They can recognize things like numbers and identifiers and email addresses and stuff like that. The context-free grammars that we've been looking at today, they can recognize things like expressions in most programming languages. There's a few caveats that apply that you don't need to worry about too much. So that and every context-free grammar is capable of representing the things that regular expressions can represent, but not the other way around. It's a hierarchy. There are things that a context-free grammar can represent that regular expressions can't. And so context-free grammar is just a more powerful way. Now you might say, well, why don't you just use context-free grammars all the time? They're a bit of a sledgehammer for a lot of jobs, and so people use the simplest one. In particular, regular languages use finite state machines. They're super simple to use. Whereas context-free grammars, you can see that parsing we're doing, it's quite a puzzle, and the algorithms for parsing are quite complicated and can be a little slower. So you use the lightest weight one possible. Now that whole hierarchy is actually there's more in the hierarchy, and it's named after a guy called Noam Chomsky. Chomsky's from MIT, is famously campaigned, for human rights and things like that. But he has also worked a lot in language. Fun fact: he gave a speech at Canterbury back in 1998. But his hierarchy is roughly like this. So at the bottom of the hierarchy, the top of this list, is regular language. They're the simplest ones. They're nice and easy to use. They're easy to implement. Then context-free grammars, which pretty much are good enough for a lot of the things we do with programming languages. There's a few variations in there, different kinds of context-free grammars. But then further up the hierarchy, there's a thing called context-sensitive grammars. You don't need to worry about those for NCA. They're a lot fiddlier to achieve. And then recursively enumerable, don't worry about that, but it basically means anything that can be computed. So that's the most powerful way of expressing things. So this hierarchy, it's not just about programming languages and rules and things like that, but it actually gets to the philosophy of what can computers do, what are the limits of computing and so on. And for each type of grammar, for each level of the hierarchy, there's a machine we use. So we used finite state automaton for regular languages. There's a thing called a push-down automaton. You don't need to worry about it, but that's what we use for context-free grammars, and more complicated ones, right up to the Turing machine, the most powerful kind of representation that we have. But that's for another day. Turing machines get used in other aspects of computer science as well, when we're reasoning about what we can and can't do. That's a really quick overview of things. That's the stuff that we touch base on. There were a couple of questions. Let me just bring them up for myself, about some of the questions that students might ask. So one is that in the standard it says things like justify the predictions that you make. The neat thing with these is it's really easy to make predictions. If I give you a finite state machine, you can predict what will happen inside it. But also at the level of making predictions about what it will do, we can characterize these things in terms of, odd numbers of A's and even numbers of B's and all that sort of stuff. So the students, if they get a lot of experience playing with these things and working with them, they can make predictions about what they will do, and sort of try and characterize those machines. There's also potential improvements. Two ways that can happen. One is that if you're given a particular finite state machine or context-free grammar, it may have things in it that are unnecessary. If I go back to one of the grammars that I had back here, so I've got S goes to SS or S goes to ASB. If I change that to S goes to ASSB, as well as, if I add one that's A goes to ASSB, that doesn't add anything to what it can do. It would be a waste. And so, with a bit of experience, your students might spot that there are things that aren't necessary in there. That's one possible improvement. And also, in terms of particularly less obvious implications, there are variations on these, and particularly finite state machines. And in the chapter, we talk about some other variations on them. They don't need to learn about all those variations, but they should be experienced enough that if they see a slightly different way of presenting them, they can make sense of those new formats. So, that's helps to deal with those kind of questions. The main thing is, if they get quite a bit of experience playing around with these puzzles and challenges and get familiar with the hierarchy and how everything relates, then this is a pretty self-contained topic. They've just got to learn the language and get a bit of experience with it. It's not a memorization thing. It's about doing things and getting the feel of what's going on. It's a fundamental idea in computer science. It's compulsory at a lot of universities. It might seem very philosophical and abstract and so on, but it really gets to the heart of, the really cool stuff that happens on computers and how to do powerful things. It's actually mainly about being lazy. We can just write a few production rules instead of having to write a whole program that does things. Ultimately, what happens is once we've written the productions and so on, that gets given to a system that automatically generates the programming language for us. So most programming languages weren't written by a programmer. They were written by a computer that was given a set of productions. Now we're getting into all the philosophy too about, can computers program themselves? Well, there's a whole lot of stuff to explore there. I'm getting carried away. That's what we got to discuss today. Good to have some time with you. Ka kite anō.